Welcome back to ECE 501B. This is our lecture immediately preceding the break, and what I want to do today is remind you of a few things that are coming at us after break, and one of those is homework number 8. Your project will be due on the 9th of December. Your homework 8 is due on the 7th, and our final exam is on a Tuesday from 6 to 8 p.m. on the 15th of December. Today what I want to do is finish up Chapter 7 material, and we'll start that by finishing up our proof of polar decomposition, where polar decomposition is this generalization of polar representation of a complex number. We have a direction, that's our isometry, and we have a scaling, which is our positive operator, which we are now using to be, or defining it to be, the positive square root of t adjoint t. That will actually lead us naturally into this new term, singular values, which are in fact the eigenvalues of this operator, square root of t dagger t, and we will illustrate that with an example. Then beyond just having or seeing singular values, we can actually use those to help us decompose any matrix, not just a square matrix, but any rectangular matrix, into this three-part decomposition or factorization. We have U, sigma, V transpose. U is made up of vectors that are orthonormal. V is also made up of orthonormal vectors, and sigma contains it has a main sort of block which is diagonal, and the diagonal entries in that sigma block or subblock are the singular values. And we can separate U and V into two pieces. One piece will be, or each of those two pieces in U will correspond to the range of A and the orthogonal complement to the range of A. And the two-part separation of V will parameterize or find an orthonormal basis for the null space of A and the orthogonal complement to the null space of A. And we'll try to illustrate that with some examples. But this is a very powerful decomposition, the singular value decomposition, and although we may not spend a lot of time on it, it's very important, and I think it's a very strong concept to understand, and you'll benefit, I think, from knowing as much as you can about the singular value decomposition. I want to just remind us of where we've been, so I'm going to scroll through some of this material a little bit quickly, but it's essentially stuff we've already, or material we've already covered. Theorem 741 is the polar decomposition. That says if we have a linear operator on some vector space V, then there exists an isometry S, which is also an operator, and that's a square operator. Well, that's redundant, but it's an operator on a vector space V such that the original linear operator T can be factored into an isometry and this positive operator, square root of t dagger t. We started with the proof of that, and we only made it partway through, but I'm going to essentially include that material, but I won't step through it line by line. The first thing that we did is we actually demonstrated that the square root of t dagger t preserves the scaling properties of t. And that was the first part of our proof. And that's good because S is the isometry. That's only conveying directional information. It's not going to influence the scaling, which means that if t scales in any way, shape, or form, we want that positive operator, the square root of t dagger t, to capture that. And that's what this first equivalence of norms conditions actually allows us to conclude. Then we want to show that S is in fact an isometry, and we're going to actually build up S in two pieces. One piece, which we are calling S sub 1, takes the range of this new positive operator, square root of t dagger t, into the range of t, and then we will extend S1 via another isometry S2 to produce the full isometry S that we need to form this factorization or polar decomposition of t equaling S square root of t dagger t. We showed that S1 was actually well defined by checking the uniqueness of the map. So that means that S1 will be well defined if this map is unique, which says that if we operate on a vector V1 with the square root of t dagger t and operate on a vector V2 with that same operator, then that must mean that t operating on V1 must equal t operating on that consistent vector V sub 2. And we showed that last time, and this is the proof of that statement. We essentially compared TV1 with TV2 by taking its norm. We used the linearity property of t. We remembered that we'd already demonstrated that we could preserve the norms between t and the square root of t dagger t, and that allowed us then to replace t with this square root of t dagger t. We could then use the linearity property of that map, and that allows us to conclude that what's inside that norm must be the zero vector, which now says that if that's the zero vector, we can add tv sub 2 to both sides to produce tv1 is equal to tv2, and that then says that that particular map is unique. Then at the very end of our last meeting, I said we need to check the linearity of the map, and linearity, as we now know from this course, consists of two pieces, homogeneity and additivity. Here I'm just writing those down or showing that indeed we are preserving the linearity of the map. S1 is then defined to map the square root of t dagger t AV, or any vector u, into t of that arbitrary vector u. Here we're writing that vector u as AV. The homogeneity property of our original map t allows us to pull out the A, and then reusing the definition of that isometry S1, or how we defined it, then we can see that in fact we do have a map that is homogeneity, or satisfies the homogeneity property. Additivity is very similarly done. We just use the definition again and the linearity properties of the original map T, and then reapply the definitions, and we end up demonstrating that indeed S1 does have this additivity property. So it is a linear map. Now what we want to do is show that S1 is an isometry, and we will do that by showing that the norm of S1u is equal to the norm of u for all vectors u that are in the range space of this square root of t dagger t, and we'll do that by using equations 742 and 743. So there are the two facts or statements. We have the norm preserving property of this positive operator square root of t dagger t, and we have the definition of this map S1, which we've now shown allows us to have a well-defined map, and it's a linear map. Now what we want to do is show that indeed it is an isometry. And remember what the definition of an isometry was, and that was that this norm of S1u is equal to the norm of u for all u. Let's see if we can then do that. It's not very long in terms of demonstration. We're just going to apply 743, which says if we take the norm of TV, well, TV by 743 is equal to S1 operating on the square root of T dagger T V. So this is just the application of the expression in equation 43, but now we can equate that left-hand side, the norm of TV, from equation 742 to equal the square root of T dagger T times V, where this equality, maybe I should put it with respect to the equality symbols in both sides. We're moving from this left-hand expression to this right equation using 742. But now if we look at what's actually happening, S1 we could say is being applied to some vector, which is in the range space of the square root of T dagger T, and that's the same as this vector U. Then if we look at what's in the last two, or those final two terms in that equality expression, we see that that is saying that S1U, the norm of that, is in fact equal to the norm of U, and that's on the range space of the square root of T dagger T, since that's where U was falling. From that expression, we can see that since it's true for all U in the range of square root of T dagger T, S1 is injective, on that range, and if that's the case, then it has a trivial null space, and we can now conclude that the dimension of the range of this square root of T dagger T is in fact equal to the dimension of the range of T. If those two ranges, or I'm sorry, if those two dimensions are the same, that then says that the orthogonal complement to those two range spaces have the same dimension also. So that now we can say that the dimension of the range of the square root of T dagger T perp is equal to the dimension of the range of the orthogonal complement of T. So now we have the dimension of these two ranges of these orthogonal complements of the same size, and we can now find orthogonal basis vectors, and I should say orthonormal, so we've now normalized those orthogonal basis. We now have an orthonormal basis on both of those, so now we have the plural. We have one orthonormal set of basis for the range of T dagger T perp, and another set of basis vectors orthonormal on the range of T perp. The orthonormal basis on the range of the square root of T dagger T perp and the orthonormal basis on the range of T perp have the same length, or those two, the dimensions of those two vector spaces or those two range spaces are the same. Now let's select some basis vectors, or let's choose E1, E2 up to E sub m to be the orthonormal basis on the first range space, which we will call the range of the positive square root of T dagger T perp. And let's now select another orthonormal basis set, again of the same length, on the range of T, or the orthogonal complement to the range of T. We know that they're the same length. We can now find an orthonormal basis for each of those spans. Now what we want to do is actually define another map. Let's now define another map, S sub 2, that will actually rotate any vector created using the orthonormal basis on the range of the square root of T dagger T perp, which would then be, let's say, A1 E1 plus A sub 2 E sub 2 plus A sub m E sub m. That's any vector in that space. And let's now define S sub 2, the other map, such that it rotates that vector into another vector that is combined using the same weightings of the other basis vectors. That's how we are now defining this new map. S sub 2 then maps from the range of the square root of T dagger T perp to the range of T perp, and make sure that it's clear that the weights on those two basis vectors are in fact the same. The weighting coefficients which are the A1, A2, A sub m, are the same. So that now we have basically rotated from one vector into another vector by means of this newly created map, S sub 2. And the vector, we could say, is W in the range of square root of T dagger T perp space, and then it's some other vector in the perpendicular or the orthogonal complement of the range of T. But if we look at this from the definition of S sub 2, we can now draw some conclusions. We can look at the norm squared of S sub 2 on this vector A1 E1 plus up to A sub m E sub m. Let's say the square of that. But by the definition of S sub 2, we know that what's inside that norm squared expression is equal to A1 F1 plus A sub 2 F2 plus dot 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 plus A sub m F sub m squared. That's how we defined S sub 2. But we know that far right-hand side the norm squared. Remember, F1, F2, F sub n is an orthonormal basis. And from proposition, I know you have all of these propositions memorized, but I'm trying to remind you of what we are now going to use. Now remember that the F's are orthonormal, and if we wanted to know what's the value of that norm squared, we could say, well, that's just the absolute value of those weighting coefficients, the sum of those weighting coefficients, absolute value squared. But what does that equal to? We could say, remember, this vector was maybe W. Well, if we looked at what the norm squared of W would be, it would be exactly what that black expression is of these weighting coefficients, because the E's are also orthonormal, meaning we can now state that this right-hand side, or this most recent equation, is in fact W squared. But now if we compare this with this, which they are equal, we just kept finding equal expressions all along, now we can conclude, therefore, S sub 2W is equal to the norm of W. Well, maybe I shouldn't have used W, but that's with. Maybe I'll write out with here. With W, and where is W living? That's now an element of the range of the positive square root of T dagger T, its orthogonal complement. And if that's the case, if we have this equality of S2W with W for all W in the range space of T dagger T, now we can say that S sub 2 is injective and an isometry. Now we have, from before, we defined S1 to take us from the range of square root of T dagger T. Where did I define that? Right here, we were saying here is how we are defining S1. It's taking us from the range of the square root of T dagger T to the range of T. It's rotating us between those two spaces. Now we have another S sub 2 that's rotating vectors on the orthogonal complements to the previous spaces. We can now use those via our direct sum decomposition to actually conclude or say now, or to create or build the operator that we want, which is the S. So now we want to define the operator that we were starting to, or wanting to end up with initially, which was S. That is, we have S1 on the range of this square root of T dagger T. That's where S1 is true, or working, and S sub 2 is this rotation on the orthogonal complement to that. So it's now S sub 2 is rotating, or it's forming this isometry on the range of the square root of T dagger T orthogonal complement. And those two spaces are orthogonal. And that now allows us to have this direct sum relationship, because there is a direct sum relationship between the range of this square root of T dagger T and its orthogonal complement, then we can say that any vector in our original vector space, let's say little v in our original vector space, capital V, we can now decompose capital V into a direct sum decomposition with one set of vectors living in the range of the square root of t dagger t and the other in the orthogonal complement to that set. So any vector V can be written as V, little v, is equal to U plus W, with U coming from the range, or living in the range, of the positive square root of t dagger t, and W in the orthogonal complement to that. That allows us then to look at what happens when we have SV. Well, now, because of this orthogonality between S1 and S2 and U and V, we can now say that SV we want to define. That's how we are defining S. So now define an operator S such that SV is equal to S1U plus S sub 2W. And we want to make sure that that now works for us. So if we now consider S, this factorization of our original linear map T, as S square root of T dagger TV, then we can say, oh, if we have that, S operating on square root of T dagger TV, this piece right here lives where? This is our original definition of our map T, but inside the square brackets, where does that vector live that will be operated on by V? Well, this is just a vector in the range of this square root of T dagger T. And that, in fact, says, oh, if we have an operator, a vector in the range of T dagger, the square root of T dagger T, that now is only going to be impacted by this piece that's in the two-piece decomposition of S. So that now we have S square root of T dagger TV is then equal to S1 positive square root of T dagger TV. But that, as we just showed in red, can be written as TV. And this decomposition since that's how we defined S1, we said S1 needs to be defined to produce these two right-hand side equalities, and that's now going to be equal to the leftmost equality, and this decomposition works for all vectors V in our original vector space. So we know that S can be defined to create this map TV. What we want to verify now, that is the fact that S is an isometry. We know that it's going to give us the correct mapping in terms of vectors in the right way, but we want to now show that, or conclude, is S an isometry. If we look at the norm squared of SV, then the way that we are defining S, that's made up of S1U plus S sub 2W. That has to be true by the way that we've defined S. And now we can say, well, norm squared is just the inner product of the argument of that norm squared piece. So we now have the inner product of S1U plus S2W with itself. And that now gives us 4 inner products. We have S1U with S1U. We have the last two, S2W with S2W. Plus, we have S1U inner product with S2W. And we have S2W inner product with S1U. But remember what S1 and S2 were doing and what U and W were relative to V. U and W are orthonormal. Or maybe I should just say orthogonal, because those could be scaled amounts. So U and W are orthogonal. But we also know that S1 and S sub 2 preserve inner products. And they also preserve this orthonormality or orthogonality. So S1 and S2 are isometries, and they preserve orthonormality, which means that they would preserve orthogonality, and that's coming to us from theorem 36, which now allows us to say that the vector S1U is orthogonal to the vector S2W, which now says that this particular inner product goes to 0. Similarly, S2W, that vector, is orthogonal to the vector S1U, so that goes to 0. Now we have the norm squared of SV equaling the right-hand side, which is really just the norm of S1U squared plus the norm of S2W squared. What we've now shown is that SV squared, that norm, is equal to the norm of S1U squared plus the norm of S2W squared. But again, how did we create or construct S1 and S2? We constructed those to be isometries, or we've now shown that they are isometries earlier in today's material. So those were isometries by construction. If that's the case, then we know that SV squared, if S1 is an isometry, then we know that that's equal to, well, let's just write it down. This is what we're starting with from above. But we know since S1 and S2 are isometries that S1U is the same, that norm is the same as U's norm, and S2W is the same, that norm is the same as W's norm. But now, remembering that U and W were orthogonal to each other, we can then conclude, since V was made up of U and W, we could again invoke Pythagorean's theorem to show that, oh, U, the norm of U squared plus the norm of W squared gives us the norm of V squared, and looking at this piece equaling that piece now says that S indeed is an isometry. And that finally allows us to conclude this proof of the polar decomposition. What have we done? So now we have shown that any linear operator can be decomposed as a product of an isometry and a positive operator. And we can understand what these two classes, how they work. We now have separated any linear operator into a factored form where one factor is this positive operator and the other factor is an isometry. We can understand how these two classes of an isometry and a positive operator work. Which then says, so we can apply that understanding to gain knowledge of any general operator. We can now separate any general operator into two pieces, a scaling piece and a direction piece. What we have to remember is that note that basis where these positive operators and isometries, where these operators have nice representations, may not be the same. And we can also view as a statement about matrix factorization. Meaning any matrix So we were talking about operators, but we know the matrix representation of those operators. We know that we can factor that operator into two different parts. One is a positive operator, one is an isometry. And we can look at the matrix factorization of those two operators, which says that any matrix now, since we've now looked at the matrix representation of those operators, any matrix can be factored into two matrices. Where one matrix factor has eigenvalues with magnitude equal to 1, that corresponds to the matrix representation of this isometry. And with the other matrix, which corresponds to the positive operator or the positive square root of t dagger t, the matrix representation of that, one matrix factor has non-negative eigenvalues. And what we now want to do is sort of play off on that second matrix in polar decomposition. The positive operator is this positive square root of t dagger t. And we want to look at that a little bit more carefully now. We call the eigenvalues of this positive operator of the square root of t dagger t, we call the eigenvalues of the square root of t dagger t the singular values of the original operator t. And we can make a couple of comments about those singular values. Since the positive square root of t dagger t is positive, which again, that's maybe a overstatement. They are non-negative. So since this is a non-negative matrix, or I guess we've called it a positive matrix, so let's just keep with that terminology. Since the positive square root of t dagger t is positive, singular values of this matrix, or of this operator t, are always non-negative. And if we have repeated eigenvalues in that positive matrix, we need to repeat each eigenvalue of the square root of t dagger t the number of times as the null space of this operator positive square root of t dagger t minus, let's say, lambda sub I times. where if we wanted to, this we could say for each lambda sub I, maybe that eigenvalue is repeated m sub I times. Let's look at an example of singular values, and this is coming to us in the second edition of Axler, starting with equation 45 in chapter 7. That starts with a linear operator, t, and it's operating on a 4 vector, subscript with, or z subscripted with 1, 2, 3, and 4, and let's say that that linear map maps to 0, 3, z sub 1, 2, z sub 2, and minus 3, z sub 4. I hope by this point in the semester it's pretty easy to immediately write down what the matrix representation of that linear operator looks like. It's now a square matrix, and if we operate on a 4 vector and generate the 0 in the first component, then we must be weighting those 4 components in the original vector z1, z2, z3 with zeros. We must be weighting that input vector with a 3 on the first coordinate or component, a 2 on the second component to give us the third component of our output, and finally we weight the fourth component with minus 3. If that's a matrix, now I want you to just remind yourself what the eigenvalues, because of the special definition of that linear operator, the eigenvalues are pretty easy to find, I hope, by inspection. It's lower triangular, which now allows us to conclude that the eigenvalues are on the diagonal. We have 3 eigenvalues at 0. So we have an eigenvalue at 0 repeated 3 times, and we have an eigenvalue of minus 3. What's the matrix representation of the adjoint? Well, if we're dealing with the standard basis, the basis now are orthogonal, orthonormal, which allows us now to just take the transpose of the matrix representation of T. The first row now becomes the first column. The second row becomes the second column. The third row becomes the third column. And the fourth row becomes the fourth column. And if we wanted to, we could now find the linear map associated with T dagger. We've now created it in the matrix form. Now what we're saying is that the first component is really just the second component of the input vector scaled by 3. The second component will be the third component scaled by 2. The third component will be 0, and the last component, the fourth component, will be scaled with a minus 3. If somebody asks for what that linear map of the adjoint is, that's now the linear map. But you can also now look at the matrix representation of T dagger T. And I'm just going to write that down, but I think it's pretty quick to compute or see if you just put these two matrices side by side. You're now scaling the second row by 3. The first row, yes, the second row by 3. The third row gives you the second row. It's scaled by 2. The third row is going to be nothing, and the fourth row is going to be the fourth row scaled with a -3. So if we put those in play, we then end up with 9, 0, 0, 0, 0, 4, 0, 0, nothing in the third row, and -3 times -3 in the fourth row, in the fourth column, fourth row, and there's now our matrix representation of T dagger T. That now allows us to also write down what this linear map is, or linear operator is. The matrix representation is scaling the appropriate components. We now have 9 times Z1, 4 times Z2, nothing, and then 9 times Z4. And if that's the case, then we can also talk about this operator square root of T dagger T. Since this original map was sort of conveniently defined, it gave us now these perfect squares. We can take the square root of those diagonal entries essentially and end up with scaling the first component by 3. The second component, again, we're taking the positive square roots, and by definition of the positive square root of T dagger T. And now what are the eigenvalues I'm not showing you maybe what the square root of T dagger T is in terms of a matrix representation, but I think you can see that that's just this diagonal matrix with 3, 2, 0, 3 along the diagonal. And the eigenvalues then of this map, or the matrix corresponding to that map, are now 3, 2, and 0, with 3 repeated twice. And what did we say about the singular values of the original map? We said that the singular values of our original map will actually equal the eigenvalues of the square root of T dagger T with the appropriate multiplicities. In this case, we have singular values at 3, 3, 2, and 0. And if we go back to the original map, T, what did we have? The original map T had eigenvalues of -3 and 0. And if we wanted to, so that's now the eigenvalues of T. The singular values of T are 3, 3, 2, and 0. And so we can sort of see that the singular values are giving us a scaling consistent with the magnitude of our eigenvalues of the original map. So we now have this singular values of T those are equal to the positive square root of the eigenvalues of the matrix representation of T dagger T. That's really what we're saying. And those were 3, 3, 2, and 0. And you can compare those with the eigenvalues of T, which these are the eigenvalues of the matrix representation of t. I might just comment before we go a little bit further and introduce the singular value decomposition. We've already played a lot with this linear map. It can be shown that the matrix representation of t can be factored into this polar decomposition of an isometry, which in our case for this particular matrix is 0, 0, 1, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, minus 1 times the matrix defined to be the square root of t dagger t, which is this diagonal matrix 3, 2, 0, and 3 on the diagonal. This is our S, that's our isometry, and you should be able to show that that is an isometry. This is now the matrix representation of t dagger t, which is all of this is now the polar decomposition of the matrix representation of the original map. What we want to do now is talk about the singular values. And the singular value decomposition. The singular values lead to a particular or a particularly useful decomposition of any operator. And that decomposition is in fact the singular value decomposition, which a lot of times is abbreviated as SVD.